In amorphous substances, the constituent particles are arranged in short range order. Further, opposite to crystalline substances, amorphous solids have range of melting point, which means if any amorphous substance is there, let's say it may have a melting point from 150 to 180 degrees Celsius. So it doesn't have a sharp melting point like crystalline substances. From different directions, amorphous solids are isotropic because of the randomness of the arrangement of its basic units. Amorphous substances look same from all the directions, so they are isotropic in nature. Further, crystalline solids can be classified on the basis of nature of intermolecular forces operating into 4 categories. These 4 categories of crystalline solids are molecular crystalline solids, ionic crystalline solids, metallic crystalline solids, and covalent crystalline solids. Further, we know we are having a long range order in crystalline substances, and there is a regular pattern of arrangement of particles which repeats itself periodically over the entire crystal. So basically, there is a repetition of a certain units or a pattern over a long range order in crystalline solids. So first, we are going to discuss molecular solids, crystalline molecular solid. In these, constituent particles are molecules. First, hydrogen bonded molecular solids, polar molecular solids, non-polar molecular solids. So there are 3 categories of molecular solids: polar, non-polar, and hydrogen bonded. First, hydrogen bonded molecular solids, like water we have. These molecular solids are formed by molecules that can make hydrogen bonding. Such solids are: one is hydrogen, they have hydrogen, fluorine, or oxygen or nitrogen for making hydrogen bonding. Strong hydrogen bonding binds the molecules of water into ice, that we know. We're getting ice crystals, which is a crystalline substance. Polar molecular solids, like these are formed by the polar molecules, as the name suggests. Strong dipole or dipolar forces hold these molecules together at low temperatures, pack them into solids. But remember, these forces, dipole-dipolar interactions, are weaker than hydrogen bonding, so their melting points will be lower than hydrogen bonded molecular solids. Non-polar molecular solids. These are formed by the non-polar molecules, and because of these forces are sufficiently weak, so such solids we get only when we cool sufficient to turn these non-polar molecules into a solid. Forces operating here are weak dispersion forces or London forces. Example: hydrogen, helium, argon, and nitrogen all having a zero dipole moment. And as you see on the absolute Kelvin scale, we see helium having a sufficient minus 268.9 Kelvin, roughly around 4 Kelvin temperature. This minus 268.9 degrees means around 4 Kelvin. Nitrogen around very low temperature, roughly 77 Kelvin. So that's we see these non-polar molecular solids will get at a very low temperatures. Now ionic solids. Ionic solids are formed by three-dimensional arrangement of cations and anions in a crystal lattice held by strong Coulombic forces, also known as electrostatic force. There are certain properties are there in these sort of crystalline ionic substances. They are hard and very brittle in nature. If we take this is a ionic solid, cation anion arrangements in 3D space, and they having a high melting and boiling points because of strong Coulombic forces that hold these ions together. Let's say we apply force on one side. Strong electrostatic forces, as we discussed, hold these molecules together, make their melting and boiling points very high. Again, to explain hard and brittle nature, we will take a crystal substance and we apply a force on it. What will happen? There will be slight displacement. That's what happens. The displaced part happens in such a way that the opposite charges, so the same charges comes directly upon each other, minimizing the distance. Here is a repulsive force. These all repulsive forces, try to push apart. Because of this crystal breaks open. Because of this repulsive force. That is the reason. They are very hard because it's not that easy to push away. That makes them hard. But they are brittle as well, because as soon as a single layer moves apart, here is the repulsive force that breaks it suddenly. That's why they are brittle in nature. Like charges come out over each other, and repulsive forces breaks the crystal. High melting and boiling point we already discussed. Strong electrostatic forces. Now, in solid state, ionic compounds are poor conductor. The reason is, in crystal lattice, these constituent ions position are fixed. Applying voltage, these will not move to transmit current. So we know positions are fixed, that's why they are insulator. But in molten state, salts are conductive. The reason is, on heating, these ions and cations and anions can move, thus act as a carrier of current. That's why in molten state, because of the higher mobility of cations and anions, they conduct electricity under applied electric field. Now, metallic solids, crystalline metallic solids. Metals are orderly collection of nucleuses of a particular metal atom surrounded and held together by free electrons. For example, these are metal kernels, and we have here all electrons surrounding it. These are free electrons that hold all the nuclei of a metal atoms together. That's why these is another, we can consider it like they having a inner core and submerged in free electrons. Each metal atom contributes at one or more electron toward pool of mobile electrons, which are known as free electrons. These free electrons are responsible for many of the properties of metals. And whatever the kernels we're talking about, they are nucleus plus fixed electrons. Here we see nucleus plus fixed electrons of metal, any particular metal you can see, iron, nickel, gold, silver, all follow the same properties. And free electrons are contributed by each atom of the metal towards the common pool. They have all properties, ductility, that can, we can make them wires, cold drink cans, malleability, you can make sheets out of them, because of their this free electrons and kernel. Now, because of these mobile free electrons, we having a metallic luster because they excites and shines back. Crystalline solids of nonmetals are also known as the covalent crystalline solids. They are from the formation of covalent bonds between the adjacent atom throughout the crystal. So there is a covalent bond formations between all the atoms